तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
This is the 25th lecture of this course and the 7th lecture on PN junction. In the previous lecture we have seen the reverse current voltage characteristics of a diode. In this lecture we will see the equivalent circuit of the diode under small signal conditions. So let us look at the slide which is related to this particular topic. So this is the biasing arrangement in which we measure the characteristics. So you have a DC voltage applied across the diode. Although the circuit shows a forward bias, the DC voltage VA could as well be a reverse bias. Over and above this DC voltage is an AC voltage which is superimposed. So this is the AC voltage. The magnitude of this voltage is small, so that is why the term Vm is said to be very, very small compared to the thermal voltage Vt. Now why the Vm should be much less than Vt? Well, at this point this is not clear. It will become clear when we take up the details. The frequency of the signal is omega, as shown by the equation. The small v is equal to capital V suffix m into sine of omega t. If this is the applied voltage, we will find that there will be a small signal current I, as shown here, in addition to the DC current capital I, and this small signal current I will have an amplitude, and also there may be a phase difference between the current and the voltage. So we would like to find out what kind of an equivalent circuit will explain this phase difference and will also help us to calculate the amplitude of the current for a given voltage. So the equivalent circuit of the diode will look something like this. So we would like to explain how you obtain the diode equivalent circuit as a parallel combination of a resistance and a capacitance. Now the approach that we will take for this is called the quasi-static approach. This means that we will try to derive the formulae for AC conditions from the DC characteristics or static characteristics. Now this is an important point to be remembered, that this approach gives you only approximate estimates of the capacitance and resistance of the equivalent circuit. To see in detail what is the difference between the quasi-static approach and a rigorous or non-quasi-static approach, I would suggest that you look into the reference material that is given in this particular slide. So this is an article published in IEEE Transactions on Education in November 1999. The page numbers are 328 to 330. The title of the article is Appealing Analogies for Aiding Students' Assimilation of Some Key Physical Concepts Related to Semiconductor Devices. Here, with the help of an analogy, the difference between the quasi-static and the rigorous approach of estimating the capacitance has been given. So in this course we will only do the quasi-static approach. Now let us understand what is meant by the quasi-static approach in a little bit detail. So this is a PN junction across which a bias has been applied. Let us assume a forward bias. We will derive the formula for forward bias and we will show that the formula will also enable us to get the parameters for the reverse bias. Now what we do is we change the voltage V by a small amount, so as a result of which the current I will also change by a small amount. Now when we make the change, we wait until for the new voltage the conditions in the diode have stabilized and you are getting a new current. So that is to say, for voltage V you get a current I, then you change the voltage to V plus dV, and then you wait, you give sufficient time so that the current stabilizes at I plus dI. So just as I is the DC current corresponding to the voltage V, I plus dI is the steady state or DC current corresponding to the voltage V plus dV. Now when the current changes from I to I plus dI, the charges inside the device also will change. So if, for example, you find that a certain charge Q is stored in the device for a voltage V, we will shortly see what is it that is responsible for storing a charge Q. As of now, let us just assume that if a charge Q is stored for V, and when you change the voltage to V plus dV, this charge increases to Q plus dQ. Then from these conditions now one can obtain the resistance and capacitance as follows. So you can get resistance small r as dV by di. So dV is the increment in voltage and corresponding increment in the DC or static current is di, so dV by di. And you can define the capacitance C as this change dQ in the charge because of the change dV in the voltage. So this is the meaning of the quasi-static approach. Okay. So we are making a change in the voltage and we are estimating the changes in the current and charges because of the change in voltage, but we give sufficient time for the effects of the change to stabilize. Okay. So for example, this resistance equal to dV by di you can represent graphically as follows. This is your forward current voltage characteristics, where I is on a linear scale and voltage is also on a linear scale. At some voltage V you make a change dV, so this is the change dV, and the corresponding change in current is di. So you note this change in current di, and this dV divided by this di is the resistance. So basically it is the slope of this curve, DC curve, at any point. Similarly, one can sketch the charge Q as a function of voltage V, and then one can take the slope of that and one can obtain the capacitance dQ by dV. So this is the quasi-static approach of determining the resistance and capacitance. Now we can quickly estimate the resistance using this formula, because we know that the ideal diode equation is given by I equal to I naught exponential of V by Vt minus 1. So differentiating this, we get di by dV is equal to I naught exponential V by Vt upon Vt, which we can write as the numerator I naught exponential V by Vt is I plus I naught from this equation. So is I plus I naught upon Vt. So di by dV is nothing but 1 by small signal resistance R. So this is the formula for small signal resistance. Now for forward bias, generally the current I is much greater than I naught. So we can write R is approximately equal to Vt by I for forward bias. On the other hand, what you see is that for reverse bias, the current I will saturate to minus I naught for reverse bias is more than 3 times Vt, and therefore you find from the formula that the small signal resistance of the diode for reverse bias is more than 3 times Vt would be infinity, because the numerator is 0. Okay, so we can write R is tends to infinity for reverse bias Vr greater than 3 times Vt. Now this is true for an ideal diode. Please note that we are deriving this for an ideal diode. In a real diode, you will find that this small r will not be infinity, because as we discussed, the reverse current increases with voltage, because the reverse current in practical diodes, for example in practical silicon diodes, is because of generation within the depletion layer, which goes on increasing because of the increase in depletion width with voltage. So in that case you will have a finite non-zero conductance or non-zero di by dV on the reverse side, therefore resistance will not be infinity, it will be of the order of hundreds of kilo ohms or higher. Okay, so what we are doing here is for ideal diode characteristics. Now how do we determine the capacitance of this particular diode under small signal conditions? Now before doing this, let me explain why the capacitance and the resistance both should be regarded as in parallel. Please note that the voltage V that is responsible for the current I and the charge Q is the same. So since the resistance and the capacitance are due to a common voltage V, that is the voltage across both the resistance and capacitance is the same, and therefore it follows that the resistance and capacitance should be shown to be in parallel. Okay, so this point should be understood. Now returning to the estimation of the capacitance, what we need to do, as is clear from here, is to derive a relation for the charge Q as a function of voltage V. Okay, in the same way as we have a relation between the current I in response to V. Let us see how we determine the charge Q. Here we have shown the conditions in a PN junction under forward bias. This is the space charge region and these are the conditions in the neutral region. This is the first time we have shown both the electron and hole concentrations in the neutral regions on a linear scale. That is why you will find a cut shown here, because if we use the same scale we cannot show both majority and minority carriers. The reason we have shown both electrons and holes in a given region on linear scale is that we must recognize that the excess hole concentration, which is shown by this shaded area in the N region, is exactly compensated by the excess electron concentration, which is the area under this portion. So when the P region injects holes into N region, these are the injected holes, the negative terminal injects electrons to compensate for the holes so that charge neutrality is maintained. So this equality in the holes and electrons is clearly seen when you plot it on a linear scale. Similar conditions exist here also. So these are the injected electrons from the P side. To compensate for this, you have holes injected from the positive contact. So we will be shading the positive charges in the device. Okay, so these are the extra positive charges, excess holes on the p side. So dotted lines show the equilibrium condition. Now come back to the space charge region. Here, corresponding to the equilibrium condition, the space charge region would have looked something like this. The width of the space charge region would have been longer. So the distance between this dotted line and this dotted line shows the space charge region width under equilibrium, and solid lines show the conditions for the applied voltage, that is V, forward voltage V. So here we find that this is for V and this is for V equal to 0. So we find that the depletion region has shrunk for the forward bias V, or in other words, the width of the quasi neutral region has increased on either side. Okay, so this is the shrinking of the depletion region, which represents also the extension of the quasi neutral end region. So equilibrium quasi neutral region was between this dotted line and this end, whereas for applied bias it is between the solid line and this end. So we can say that the shrinking of the depletion layer has caused expansion of the quasi neutral regions, and in other words, therefore, what has happened is that extra electrons have been introduced in this n region and extra holes have been introduced in this p region, so as to compensate for the ionized impurities here and there to create charge neutrality. Now when you have extra electrons here in the quasi neutral regions, obviously some holes will be there which are minority carriers. Similarly, some electrons will also be there, but we neglect the effect of these electrons on the p side and holes on the n side because they are minority carriers. As far as the depletion layers are concerned, we are neglecting their effects. So we can say the expansion of the quasi neutral region has been because of injection of electrons from the negative terminal, and exactly equal number of holes have been injected from the positive terminal so as to extend the quasi neutral region on the p side. So this area represents the extra holes which have come in at the forward bias voltage V as compared to the equilibrium condition, and obviously this area is equal to this area, and this represents the extra electrons. So these are extra electrons. So this is how what one can say is that as compared to the equilibrium condition, because of forward bias, there has been a change in the concentration of holes and concentration of electrons. So we can write this down as follows. In the PN junction you have charges which are because of impurities which are bound charges, and you have free charges which are electrons or holes. And now the electrons and holes, they change when a voltage is applied because of so the free carrier charges change due to change in the space charge width and due to change in the excess charge in the neutral regions or quasi-neutral region. So the electrons and holes, they change in the number, but these impurities, the bound charges, do not change. So we need not take the effect of these into account, because we are defining the capacitance as dq by dV. So change in the charge is what is of interest to us because of dV, not the absolute magnitude of charges. So since the bound charge or impurities do not change with voltage, so we do not consider the effect of the impurities in estimation of the capacitance. So the changes in the free carrier charge we have indicated here in the diagram. The shaded areas show the excess holes which have come in because of the applied voltage V as compared to the equilibrium conditions. So now we can estimate the capacitance by taking the sum of these hole concentrations and then dividing by the incremental voltage. So in this case the incremental voltage is V itself, because we are comparing it with respect to equilibrium condition. Okay. Alternately, we could write down an expression for these excess holes and we could differentiate this expression with respect to voltage. Now there is one point that one must remember: while estimating the capacitance, you can either take the change in the positive charge or the change in the negative charge. So the term dq here, the term dq represents either the positive or the negative component. Okay, that is why we normally put a modulus on this particular term to represent the capacitance. The capacitance is always positive, so you can either take the positive component or the negative component. If you take the negative component, this term will be negative, so you have to take the magnitude to take the capacitance. So we will take the positive component of the charge for estimating the capacitance. Any capacitance, the positive and negative components will always be equal, because the device as a whole is charge neutral. Okay, so now let us write down the expressions for this excess hole charge. We will take the space charge region and the quasi-neutral region separately. Let us take the space charge region first. What is the formula for these excess holes as compared to the equilibrium condition? We can write this as follows. Let us represent the excess hole concentration in the space charge region as Qp suffix d. D stands for depletion. Okay, so we are calling this either space charge or depletion region. So Qp is excess hole concentration that has come in at voltage V because of change in the depletion region. Okay. So we will write here space charge region changes. So QPD, that is this particular shaded area. So that we can write as the depletion region width on the P side, that is XP minus XP0, this is the change in the depletion region, into Q into the acceptor impurity concentration there Na into the area of the junction. So this area of the junction is the cross sectional area in direction perpendicular to the board. So in this case here, this width is Xp and this width is Xp 0. Okay. So in fact this formula should be written xp0 minus xp, because xp0 is more than xp. So this is the qp, whole charge. Now what one can do is one can differentiate this with respect to voltage. The voltage dependence comes because of the dependence of xp on voltage, depletion width on the p side on the voltage. So you can differentiate dqpd by dv, and we can write this as q times, and we have to take a modulus. So q na into a into d xp by dv. There is a negative sign here because minus xp. So this would represent the capacitance contribution due to the space charge region. Normally this contribution is shown using a symbol C suffix depletion, okay, because this is a capacitance due to changes in the depletion layer. So one can evaluate this by substituting the expression for xp. I will leave it as an exercise for you to derive the expression for the capacitance C depletion by substituting the expression for xp and differentiating it with respect to the applied voltage. What I will do here is I will derive the final expression by a different method which is much simpler and which is more physical rather than mathematical. Now this method can be understood as follows. You take only the increments, okay, and let us see how the incremental picture of these charges looks like. The incremental picture can be drawn as follows. So this is the p plus side, this is the n side, this is the p-n junction, this is the incremental hole charge, and this is the incremental electron charge. So this is the so called QPD. Now if you take this increment between any two voltages, so that is this edge corresponds to voltage V and this edge corresponds to V plus dV. So this is the increment dqpd because of increment dV. Then this thickness of these regions will be very, very small. So here we have shown these changes with reference to the equilibrium condition. Okay, so this V, this equilibrium. So supposing this V is very small as compared to equilibrium, then that would be, this V is nothing but the incremental voltage dV. Or alternately, we can draw the picture for any two voltages which are different only by an incremental voltage dV. That is what we have done here. Okay, so for one voltage V, this is the picture, and another voltage V plus dV, depletion region has shrunk, this is the picture. dV is very small, so this thickness is very small, okay, and this is the corresponding picture on the P side. Now this picture corresponds to that of a parallel plate capacitor. You can very easily see this is like a parallel plate capacitor whose distance is between the charges is nothing but the depletion region XD, and the charges are on this side. Okay, this is an incremental picture. Please remember, this is an incremental picture because we are interested in incremental capacitance, which is dq by dV. So incremental picture of the changes in charges at the edges of the depletion layer is similar to that of a parallel plate capacitor, the distance between the plates being XD. So we can very simply write this particular capacitance, that is the depletion capacitance. We can show that this will be equal to epsilon into A by XD, Okay, this is a capacitance because of a parallel plate capacitor, plate separation XD. So this is a physical approach to determining the equation. So you can mathematically do this expression, work out, and then show that it is nothing but epsilon A by XD. Now one clarification, this is the change in the depletion layer charge. So it is shown on a negative side because on the p side the space charge is negative, on the n side the space charge is positive. Now one might wonder that how the change in the negative side has been shown as a whole dqpd, right, change in the positive charge. Please note that what we are showing is the magnitude of the change in the positive charge. So the negative charge is decreasing in magnitude. Please understand this. Come back to this figure. This is the negative charge. When you apply more and more forward voltage, the negative charge decreases. So what is shown is the change in the negative charge. Okay? So decrease in negative charge means increase in positive charge. So if you want to show that more accurately, then you must show the dqpd as a rectangle on this side, okay, and dqn, that is the change in the electron charge on this side, as a rectangle here. Okay, here we must understand that what we are talking about is the magnitude of dqpd. So this is the magnitude, the shaded area. We don't care about the sign when you are talking of the magnitudes. Fine. So this is how one can estimate what is called the depletion component of the incremental capacitance of a diode. Now we should see how we can determine the diffusion component of the capacitance, that is the capacitance or incremental capacitance because of charges in the quasi-neutral regions. This particular capacitance is called diffusion capacitance because these charges, okay, in the neutral regions contribute to the diffusion current of the diode. Now you might have a doubt, how does this charge contribute to diffusion current? Okay, this is the majority carrier charge. Well, this is an important point. You must note that this charge is equal to this charge, okay, because this region should be quasi-neutral. So sum of these two charges, which are the excess holes in the neutral regions, is equal to sum of these two charges, these areas, okay, and you know that the minority carrier charge, excess minority carrier charge, contributes to the diffusion current on the p sides, just as the excess minority carrier charge or hole charge contributes to the diffusion current on the n side. That is why we can estimate the capacitance by summing up these two areas, okay, and therefore this capacitance is referred to as the diffusion capacitance. So now we will discuss the estimation of the diffusion capacitance. So the diffusion capacitance can be written as differential of the sum Qp plus Qn by dV, where Qp is this charge, which is the excess charge due to minority carrier stored on the n side, and Qn is this charge, the area under this excess carrier concentration stored on the p side. This is excess electron charge stored on the p side. Please note that actually we want to find out the total number of excess holes because of voltage V, which is this plus this. But since this area is equal to this area and we know the distribution of minority carriers, because the distribution of minority carriers can be solved very simply using the continuity equation. Therefore, instead of summing up these two, we are summing up these two, okay. So one should not think, why are we summing up the electron charge and the hole charge? Electrons are negatively charged and holes are positively charged. So we are not summing up negative and positive charges, please understand, we are summing up magnitudes only, okay. Actually we are summing up the whole charges on the two sides of the quasi-neutral region, but since the magnitude of the whole charge, excess whole charge on the p side is same as the magnitude of the excess electron charge on the p side, we are summing up these two, and these two can be written down easily. Now this is where you must understand the quasi-static approach. Why the word quasi-static is being used? Because please note that these distributions which I have drawn here, these are known for the static or steady state conditions. They are exponential, and therefore the area can be easily determined once you know the distribution. Now in steady state conditions the distribution is exponential because you take the continuity equation for the minority carriers and then you set the rate of change of the minority carrier concentration as 0. For example, if you want to get this exponential distribution, then you take the continuity equation for holes and you are going to set dou p by dou t in the continuity equation to be 0. Let me write that equation here to show this. So dou p by dou t is equal to minus 1 by q dou jp by dou x minus delta p by tau. This is the continuity equation for holes on the n side. To get the distribution of holes, you are going to set this equal to 0 under steady state conditions. Now you are going to use this exponential distribution obtained under steady state conditions to estimate the changes in the charges also under non-steady state or time varying conditions, the voltage varying with time conditions. So which means that you are setting this dou p by dou t not exactly equal to 0 but approximately equal to 0, so that you can still use the continuity equation setting these terms equal to 0 and get the exponential distribution and then work with that. So this approximately equal to 0 means quasi-static. Please note that strictly speaking dou p by dou t when the conditions are varying with time is not equal to 0, okay. That is why strictly speaking the distribution of the holes will not be exponential. So coming back to the estimation of Qp and Qn, we can easily write the expressions for Qp and Qn by looking at this diagram and our knowledge of the distribution of holes and electrons. So we write Qp is equal to Q times delta P into diffusion length Lp into the area A of the cross section of the diode. So this is your excess carrier distribution delta P, this is the diffusion length Lp, and you know that the area under this rectangle is same as the area under this exponential, okay. This is the area that we are interested in, that is what we have written down. Now similarly one can write down the expression for Qn also. Now what we will do is, since we are considering a one-sided junction, the p side doping is much more than the n side, therefore we will neglect Qn compared to Qp. This will help us to get a simple equation for the diffusion capacitance. So we assume Qn less than Qp since p plus n junction. So with this approximation and this equation, you get the equation for C diffusion as d by dV of delta P multiplied by Q Lp into A. Now we know that expression for delta P as a function of V, that is delta P is equal to Pn0 exponential of V by Vt minus 1. So if you differentiate this with respect to V, you will get Pn0 exponential of V by Vt divided by Vt, and which you can write as delta P plus Pn0 by Vt. This term is nothing but Pn0 exponential V by Vt So you shift this minus 1 on this side, and that is how from this equation you get this is equal to this. So we can write this here. So this is equal to Q A LP into delta P plus Pn0 upon Vt. Now when you are talking about forward voltages, this delta P is much greater than Pn0. So we can approximate for forward voltage conditions or for forward bias, the diffusion capacitance C diff is Q A LP delta P upon Vt. This is approximately equal to, since we have neglected Pn0. Now we can write this term very simply in terms of the current. We know from our diode theory that for a P plus N junction, the current I, forward current I, is approximately equal to Q A delta P into dP upon LP. This is a diffusion current. We are neglecting the diffusion current because of electrons. So look back into the forward diode equation which we have derived, and you will find this equation. We can write this equation, we can multiply by lifetime tau and divide by lifetime tau, and then we can identify this term as LP square. Now this LP square will cancel with LP, one of these LP terms will cancel, and so this is equal to Q A delta P LP by tau. So from this equation of the forward current, it is clear that you can write the numerator Q A LP delta P as I into tau. So this is equal to I tau upon Vt. So this is the formula for the diffusion capacitance. This is very easy to remember because current into time is charge, and charge by voltage is the capacitance. So the characteristic voltage is the thermal voltage, and here this is the characteristic time, that is the lifetime. So this enables you to write down an expression for the diffusion capacitance very simply in terms of the forward current. Please note that this is derived under the condition that it is a one-sided junction when we neglect the electron charge on the p side. Okay. Now what happens under the reverse bias? Okay. In reverse bias, this excess carrier concentration delta P is negative of Pn0 because you have depletion of carriers in the neutral regions. So delta P is minus of Pn0, so these two terms cancel, your diffusion capacitance goes to 0. So reverse bias, we can say that diffusion capacitance goes to 0. Now this will happen for reverse bias voltages more than 3 times Vt. For reverse bias voltages less than 3 times Vt, there will be some small diffusion capacitance, but generally we operate in reverse bias voltages more than 3 times Vt, therefore diffusion capacitance is taken to be negligible under these conditions. So now we can summarize the results of our small signal analysis as follows. From the DC current voltage characteristics, wherein the current is proportional to exponential V by Vt minus 1, we get the small signal resistance R of the diode, that is shown here. So this is the equivalent circuit under forward bias. So this R is Vt by I, where the I0 term has been neglected as compared to I. Now this is obtained as the slope of this particular curve. So di by dV equal to 1 by R. Now consider the stored charge in the neutral regions. taking only the stored charge in the lightly doped region for a p plus n junction, this Qp varies with V in the same way as the current. So this is also an exponential behavior, this is also an exponential behavior. You can check this from the formula that we have derived for Qp, which was Qp equal to Q delta P Lp into A. So you can write expression for delta P and you can show that the Qp will be proportional to exponential of V by Vt minus 1. Then you take the slope of this curve and this gives you the diffusion capacitance. So dQp by dV is the diffusion capacitance. Similarly, you take the whole charge that is injected into the device because of shrinking of the depletion layer in the forward bias, okay, and that follows this particular behavior as shown in this graph. Here this particular quantity is proportional to square root of psi naught minus V minus square root of psi naught. This is because of the change in the depletion layer width. You see that QPD is negative for reverse bias because here when you apply reverse bias, this is positive with respect to this and then the depletion region expands. So the quasi neutral region shrinks. So you are extracting holes from this side and electrons from the other side. So the extracted holes is what is represented here for reverse bias. So you take the slope of this and then you get the depletion capacitance. So the depletion and diffusion capacitances are shown here. The results are that C diffusion is current into lifetime by thermal voltage and depletion capacitance is equal to epsilon A by xd, where xd is the depletion width. The depletion capacitance can be seen physically as a parallel plate capacitor. Okay, this is an incremental capacitance. It is like a parallel plate capacitor. The incremental charges are separated by the distance xd. For reverse bias, we should put exactly equal to sign. The depletion capacitance is again given by epsilon A by xd. Here xd goes on expanding, so depletion capacitance falls. We do not show any diffusion capacitance or resistance in reverse bias because, as we have said, diffusion capacitance is negligible and resistance is very, very high. Okay, so those two elements are not existing for reverse bias. For forward bias, for moderate forward bias where the devices are operated, generally the diffusion capacitance dominates over the depletion capacitance. So this quantity is negligible, okay, for moderate forward biases. Now it is of interest to look at the reverse bias capacitance or depletion capacitance for reverse bias in a little bit detail, as this quantity is useful in several applications. Since the reverse bias diode is almost like a pure capacitor without any parallel resistive component or loss component, and this capacitance varies with voltage, an important application of a reverse biased diode is that of a voltage variable capacitor. Now another application of diode in reverse bias is that we can show that we can extract the doping level in the lightly doped region from the measurement of the reverse biased diode capacitance. To see this, let us expand the formula. C depletion equal to epsilon A by xd. We write xd is equal to 2 epsilon V R plus psi naught, where VR is the reverse bias, upon Q into 1 by Nd plus 1 by Na. And then here we recognize that since Na is much greater than Nd, this quantity can be neglected, one-sided junction. We should put a square root here. And so now for the one-sided junction we can substitute for xd here, and then we can simplify and you can show that 1 by C depletion square can be written as 2 by epsilon A square Q into 1 by Nd. This is approximately equal to this quantity. So here we are assuming Nd is much less than Na. So of course we should write the Vr plus psi naught. So what we find from here is 1 by C depletion square versus the reverse bias Vr is a straight line whose slope gives you Nd. Okay? So slope of 1 by C depletion square versus Vr is equal to 2 by epsilon A square Q Nd. So if you know the area A and you measure the 1 by C depletion square and plot it as a function of Vr, then you can get the Nd. Let us look at a measured characteristics of reverse bias capacitance. This is shown in this slide. You can see that it is almost a straight line. Here Cj indicates the junction capacitance. This is another symbol that is used normally for the capacitance, Cj, and this is as a function of applied bias, so that is why it is shown on the negative axis. Okay, so these are reverse voltages. These are the values for a typical silicon diode of area 0.32 millimeter by 0.32 millimeter. Now this intercept here, if you extend this solid line and then let it intersect the voltage axis, the intercept gives you the quantity psi naught. This can be seen from this particular equation. So Vr is minus psi naught, or if you are writing instead of Vr minus V, if you write Vr plus psi naught as psi naught minus V, then V is equal to psi naught when the 1 by C depletion is 0. So the intercept, this quantity here on this slide, shows psi naught, this distance. So you can extract an approximate value of psi naught also. One can also see from this slide the typical values of the capacitances for the area considered. So the capacitances are of the order of picofarads. Okay? So what you see here is square of picofarads, but you can always estimate from here these values, and you can see that they are of the order of picofarads. Now for information, if you take the equivalent circuit for the forward bias here, since these capacitances are of the order of picofarads for areas of 0.3 mm by 0.32 mm that we have considered, the moderate forward bias, the diffusion capacitance, will be of the order of nanofarads, okay, and it can go up to microfarads for larger forward biases. Now what about the resistance, small signal resistance? The small signal resistance, as you can see, if the currents are in the milliampere range, since Vt at room temperature is of the order of 25 or 26 millivolts, this is of the order of ohms. So for 10 milliamps current, 26 millivolts by 10 milliamps, that is about 2.6 ohms. So that is the kind of small signal resistance that you get for the diode. Now before summarizing our discussion on the PN junction, if there are any questions, I would like to take them.
Sir, I have a question regarding the reverse saturation current I0. For the measured forward IV characteristics at room temperature, we calculated I0 to be of the order of 10 power minus 13 amperes, but the reverse characteristics at the room temperature show a much larger reverse current below breakdown, that is of the order 10 power minus 9 amperes. Why so?
Yeah, so your question is related to the following slides which I showed. So here, to explain this forward characteristics, we found that the I0 was of the order of 10 power minus 13 amperes. But if you see the reverse characteristics here, what you are saying is this current is of the order of 10 power minus 9 at room temperature, okay, somewhere around this. Now this is because the forward characteristics were explained using the diffusion current, okay, and I naught calculated there was the diffusion current. Now as we have pointed out, in silicon diode the generation current dominates on the reverse side as compared to the diffusion current. So though the diffusion current saturates, the generation current within the depletion layer that dominates the diffusion current goes on increasing with voltage. Now this generation current within the depletion layer is of the order of 10 power minus 9 amperes, okay. So that is why you are getting the reverse current of the order of 10 power minus 9 amperes instead of the 10 power minus 13 ampere current that we had used for calculating the forward characteristics, okay. Now since you have asked a question about the reverse characteristics, let me tell you another important aspect of the reverse saturation current. It is found that the reverse saturation current in a silicon diode doubles for every 10 degree centigrade rise in temperature, and for germanium diodes in which the energy gap of the germanium material is less than silicon, in fact it doubles for as small as about 4 to 5 degrees centigrade change in temperature. Now how do you get this behavior that the current doubles for 10 degrees centigrade rise in temperature in a silicon diode? Well, what you should do is you should write the expression for generation current and then for diffusion current and you sum it up. The total reverse current is because of generation plus generation in the depletion layer plus diffusion, okay. Now at room temperature, around room temperature, generation current will dominate over diffusion current. Generation current is proportional to Ni. If you take the ratio of Ni at two temperatures differing by 10 degrees centigrade around room temperature, you will find it is close to 2. At higher temperatures, diffusion current dominates over the generation current and the diffusion current is proportional to Ni square. At higher temperatures, let us say around 100 degrees centigrade for example, if you take the ratio of Ni square for two different temperatures differing by 10 degrees centigrade for silicon, you will find that this quantity will again turn out to be close to about 2. So this is how combination of generation and diffusion currents give rise to this kind of a behavior of doubling of the reverse current for every 10 degrees centigrade rise in temperature. Now I would like to summarize the discussion on the PN junctions. So we covered the following topics in the last 7 lectures. First we discussed device structure and fabrication. Then we idealized the structure and used the approximate simple structure for analysis. First we discussed the equilibrium picture in which we gave the distributions of N, P, J, Jp and E, and then we also considered the variation of energy bands. Then we considered the ideal current voltage characteristics for forward and reverse bias. We derived the characteristics based on spatial distributions of N, P, J, Jp and E. We showed how the analysis can be done without the aid of energy bands using the 5 basic equations. And then we also drew the energy band diagram for forward and reverse bias to show what is the advantage you gain in terms of getting information and details using the energy band diagram. Then we explained the non-idealities in real current voltage characteristics, namely the ideality factor, series resistance, depletion layer generation current and breakdown. Finally we considered the small signal characteristics where we gave the equivalent circuit of the diode consisting of resistance and capacitance for forward and reverse bias.